Hi AP students. We're on 3.2 where we're going to do a lot more with our least squared regression. A regression line is a line that describes how a response variable changes as an explanatory variable changes. Some people don't gain weight even though they overeat. Perhaps fidgeting and other non-exercise activity, NEA as we're going to refer to it, explains why. Some people may spontaneously increase non-exercise activity when fed more. Researchers deliberately overfed 16 healthy young adults for 8 weeks. They measured fat gain in kilograms as the response variable and change in energy use in calories from activity other than deliberate exercise. So fidgeting, daily life, and the like as the explanatory variable. So here are the data. So there's the non-exercise activity, negative and positive in calories, and then the fat gain that these overfed young adults had. So here's what the regression line looks like. So this all the data points, it looks pretty linear. It's a negative. It's a moderately strong correlation, right? It's not perfectly strong, but it's pretty moderately strong. And the regression line has the form y equals a plus bx. You guys are used to this probably. So a is your y-intercept and b is your slope instead of m. That's just what we use in stats. Y hat is the predicted value. So it's the predicted response based off of the input. B is the slope, the predicted change when x increases by 1 unit. The interpretation is going to be important. A is the y-intercept, the predicted value when x equals 0, not starting value. We'll show you what that means later. So in our line, we have the predicted fat gain is 3.5 pounds minus 0.00344, which is our slope. So what these mean are, if there was no non-exercise activity change, so 0, they would gain 3.5 pounds. We would predict that they would gain that. And then it's a little bit less. It's for each non-exercise activity calorie, the predicted fat gain goes down by 0.003 pounds. Does the low value for slope mean there's no relationship? Well, that is very little. It doesn't mean that there's no relationship because it's clearly decreasing, but not by much. So when we think about that, that's setting us up for the future in chapter 12. I'm not sure if that means that there's not really a relationship here because the slope is so low. If a person's NEA increases by 400 calories when she overeats, what is the predicted fat gain? So all we're going to do is plug in 400. So we have 3.505 minus 0.00344 times 400. And we'll go to our calculator. If this person increases 400 calories, then they predict that they will still gain 2.129 pounds. So what if a person's NEA increases by 1,500 calories? So now we're going to do the same thing with 1,500. So in this case, the person's going to overeat, but they're going to do 1,500 calories of non-exercise activity, and then they would actually be losing weight even though they're overeating. Well, that answer doesn't really make sense because, first of all, 1,500 calories of non exercise activity is a ton. I don't think that anybody would actually be doing that. And a lot of people, when they're working out, they never even reach anywhere near this. In general, when they're working out, nevertheless, fidgeting and just living their life. And this losing weight thing, so this answer doesn't really make sense. Okay, this 1500 calories is way off the charts. Maybe it would make sense to predict for 800 calories, but even still, we're so far away from where our data actually is that we call this extrapolation. So the number of husbands, as one person had a husband, and then over time, as you see by next month, you'll have over 4 dozen husbands. Okay, well, the data doesn't really go past today. And that doesn't really make sense. That's what's going on in this little cartoon. We can use the 400 calories as a predictor because 400 is in our data. This is called interpolating, not extrapolating like we did before. So it's interpolating because it's inside our data. And that would be okay for our prediction. So regression lines estimate the trend of the data points. There is always almost some error in this estimation. So what we have is the weights of 8 hikers and the weights of their backpack. So this is our hiker weight. So this is our biggest hiker at 187 pounds, and then they have a 30-pound backpack, which isn't the most, but basically what you're seeing is as body weight increases, the weight of the backpack increases. And that's what this line is saying. So if we use the line to make a prediction for someone who weighs 120 pounds, well, that would be okay. It's interpolating. We could plug that in. $27.196. So 27.196 is a little bit higher than the predicted value, right? For the person with 120 pounds, we predicted it would be 26, but they actually had a 26-pound bag, but we predicted based off of our line that it would be a little bit more. You see how it's under? So we overestimated the pack weight for someone who weighs 120 pounds. What we can do from here is we can find what's called the residual. Well, that would just be our actual value minus what our predicted value is, which we know will be negative 1.196. Our residual is negative because our actual value is below the line. The error of estimation by a regression line is called a residual. We calculate a residual by taking the observed value minus the predicted, like I did right here. Calculate and interpret the residuals for the people who weigh 165 pounds and 103 pounds. So we need 165 minus, and then we'll plug in 165. So 31. Well, the actual value for 165 was 35 pounds. Minus, and our residual is 31.282. So our residual is positive this time, and it's 3.72, good enough. And then we can calculate our residual for 103 pounds. Well, the actual value was 24, and then we'll plug in 103. So 25.65 for a residual of negative 1.65. So these are the errors. This one was below, this one was above. When we calculate the regression line on our calculator, we calculate the line that minimizes the residual squares. So we're going to look at an activity and I'll show you how this works in class, but I'm not going to do any more on this now. But this is where it comes from. We call this specific regression line the least squares regression line, and we can abbreviate it LSRL. We want to calculate and interpret the standard deviation of the residuals S. So what we could do is we can take all of our residuals and then find our standard deviation. Well, we'll just do it with those three for now. So 3.72, negative 1.65, and then our third one, negative 1.96. And we'll run our one variable stats on this. And then we're going to use all of them, so it's 2.6. So our standard deviation of the residuals is 2.6. We'll probably talk a little bit more about S in class, but basically when we do these calculations, we'll find S. the standard deviation of the residuals. So here's some interesting facts about the least squared regression line. It passes through the point x bar, y bar. So the mean of the x and the mean of the y is where it will pass through, which makes sense because we're minimizing the residual squares and this is our middle value. Its slope is r times standard deviation of the y's divided by the standard deviation of the x's. Its y-intercept can be written in this form. Y bar, right, our mean of the y's minus the slope times the mean of the x's. And this line is very sensitive to outliers, so often we will ignore outliers when we can. Let's talk about this r squared, the coefficient of determination. So r's correlation coefficient, and it measures the strength of the linear relationship. We call r the coefficient of determination. It measures the percent of variability in the response variable that is explained by the x variable. So if we go back to our Hiker data. So this is our Hiker data, and these are the squares of the residuals, residual squares. We see that r squared is 0.63. So we could say that 63% of the variation in backpack weight can be explained by the linear relationship with body weight. So basically what this is saying is body weight and backpack weight are related with this linear relationship. 63% of this variation occurs because of those two variables, while the other percent would be from other variables. Okay, this is really a Mad Lib. The easiest way for you guys to do well on this is to just use this like our interpretation for confidence intervals. We use it and we will move on. We're not going to study this too hard.